So last section we're going to look at this week is 6-5. So we'll split it up between today and tomorrow. Totally different than the first half of the week. We're now going to be looking at right triangles. Okay, so we're still going to look at trig functions, but we're not visualizing them on a graph anymore. All right, so since we are going to be looking at trig functions of acute angles, we're going to be looking at them in what we call right triangles. So just as kind of a quick reminder, what does it mean if a triangle is a right triangle?
It means that one of its angles are 90 degrees.
Right, it means one of the angles is 90 degrees. Okay? And what do we call the side that's opposite the 90 degree? Has a special name?
The hypotenuse.
Hypotenuse. And what do we call the other two sides that are not the hypotenuse? Yep.
Opposite and adjacent.
Okay, so they do have specific names, opposite and adjacent. We'll get to that in a little bit. But what about, I'm thinking of a word that describes both of them. Yep.
Legs.
The legs, yeah. And one of the legs is opposite and one of them is adjacent. Okay, what do we call, normally we use these letters to represent the sides. What are the letters that we use in a right triangle? Yep.
A, B, and C.
Yep, and what are the A and the B?
The legs.
The legs and the C?
The hypotenuse.
Hypotenuse, yeah. It's not that you have to use A, B, and C. That's just the convention that we use most of the time. Okay. So there's a diagram of everything we just said. Remember that if an angle is acute, it has to be between 0 and 90. And what do all the angles in a, we'll call it a two-dimensional, like a Cartesian plane triangle, what do all the angles have to add up to? Yep.
180.
180, yep. So if you've already used up 90 for the right angle, then the other two acute angles have to be complementary. They have to add to 90. And that gives you a total of 180. Okay, there's a theorem that we can use that will connect all the sides in this triangle. And this theorem helps us, if we only know two sides, we can find the third one. Does anybody remember the name of the theorem? Yep.
Pythagorean theorem.
Yep, Pythagorean theorem. And can you tell me what that is?
A squared plus B squared equals C squared.
Right, if we're referencing this diagram, A squared plus B squared equals C squared. One leg squared plus another leg squared equals the hypotenuse squared. Okay, that's the Pythagorean theorem. Why? Why does A squared plus B squared equal C squared? Does anybody know how to explain that? Yeah?
I can't think of much of an explanation, but I do know if you maybe change the triangle into like a rectangle or something, and find like a side of that rectangle, it would equal to the C.
Okay, so yeah, there are many ways you can explain why A squared plus B squared equals C squared. I'm going to show you one way, and it is going to involve drawing a picture. It's not going to involve any rectangles, it's going to involve squares. So it involves squares and triangles. So let's take a look at this picture. That's all we need to explain why A squared plus B squared equals C squared. And a few formulas for area. So what I've drawn here is basically a square and then another square inside it. Each side has been labeled. And all of these four triangles that are created by the square and then the other square that's rotated inside it are all congruent. Okay, they all have sides of A, B, and C. All right, so what I want to do is I want to find the area of the inner square. What's the area of the inner square? Yeah.
C squared.
Yeah, it's C squared. It's a square. It's tilted, but it's still a square. So it's c times c. So let's do the area of the inner square equals c times c. Now I want to do it again. I want to find the area of the inner square. But you're not allowed to use the letter C anymore. Can't do, well, you can use the letter C, but you can't say C times C. What's another way that I could find the area of that inner square? Yep.
Like a plus b in parentheses and then squared.
What would that give you?
Okay. Oh.
Well, you don't have to tell me the answer, but what, in the picture, what does that give you?
Oh, that was the area of the bigger square.
Area of the bigger square. Okay, so let's find the area of big square. And then what would you do after you find the area of the big square?
You subtract the area of the rest of the triangles.
Yeah, subtract the area of those 4 triangles, and what you'll be left with is the area of the inner square again. So let's try doing that. So let's take the area of the big square and subtract the area of the triangles, of which there are 4. All right, and since you already told me, you said to find the area of the big square, how did you do that?
The a plus b and then squared.
Right, because the length of one side of the big square is a plus b. So a plus b squared, that's the area of the big square. And then what's the area of, let's do this triangle right there. Yep.
1/2 of a times b.
So it's 1/2 of a times b. And how many of those triangles do I have?
4.
4. So I'm going to multiply that by 4. Okay. So we need to just figure out what that comes out to. And that will give us a different formula for the area of the inner square. So here's our first one. Let's figure out the second one. Okay, so when we square a plus b, we get a squared plus 2ab plus b squared. And what's the part that we're going to subtract, what does that simplify to? Yeah.
Minus 2ab.
Minus 2ab. Okay. What does the line that I have now, what does that simplify to? Yeah.
A squared plus b squared.
A squared plus b squared. And what does that represent? What is a squared plus b squared? We just calculated what? Well, what we just did all this work to figure out a formula for, like, what does this tell me in this picture?
What's the area of all the triangles? Or what do you take?
It's not the area of all the triangles. The area of all the triangles is 2ab. Yep.
It's the area of the inner square.
It's the area of the inner square. We did the area of the big square minus the area of the triangles. So this formula gives you the area of the inner square. And this formula also gives you the area of the inner square. So then, since they both give you the formula for the area of the inner square, what can we do with both formulas? Yeah.
So
can set them equal to each other because they're calculating the same thing. So c squared equals a squared plus b squared. So that's one way that you can find or prove the Pythagorean theorem. And referencing this diagram, A is one side of one leg, B is another leg, and C is the hypotenuse of a triangle. All right, so we've looked at the 6 trig functions before when we did the unit circle, where we had sine is y, cosine is x, tangent is y over x. Now we're going to look at the 6 trig functions, but we're going to do them with the words opposite, adjacent, and hypotenuse. It's really the same thing. It's just a different way of looking at it, and we're not thinking of it on a unit circle. We're going to think of it now in a triangle. Because we're working in a triangle, we're not going to have to worry about angles that are going around more than once. Okay, like on the unit circle, I might have asked you to find like the sine of 450 degrees. And you could do that, because on a unit circle, you can go around as many times as you want. In a triangle, you can't have a 450 degree angle. That's too big. So our angles are going to be much more limited in size when we deal with right triangles. So let's look at the first 3 trig functions. And the first 3 are sine, cosine, and tangent. And the sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. If you're not sure what those words mean, we will describe them a little more. We already did hypotenuse. It's across from the 90. But I'm going to explain to you what opposite and adjacent mean in a minute. Now, when I write opposite over hypotenuse, what do I really mean there? Like, I am dividing 2 things, but what about the opposite? And what about the hypotenuse? Like the color of the opposite, or how heavy the opposite side is? Like, what am I really talking about? The length of it, right. So each trig function is a ratio of a length of one side divided by a length of another side. So imagine you had something for cosine like 5 inches divided by 8 inches. When you divide this by that, what happens? Like, what would that simplify to as a fraction? Yep.
5.8 inches squared.
If we were multiplying them, it would be 5 times 8 inches squared. But we're not multiplying them, we're dividing them. So what's going to happen? Yep.
The inches just cancel out.
The inches would cancel out. So what I'm trying to show you is when you find a trig function, the ratio of 2 sides in a triangle, there is no label. It's not inches, it's not centimeters, it's not radians, it's not degrees. It's just a number without any label. That's it. 5/8. Now, when we do the next 3, what's the connection between the 3 trig functions on the right and the 3 on the left? We got to be careful with the word we use. Opposite would mean like it's the negative of it. Is that what you mean? No. And what is that called? Yep, reciprocal. Reciprocal. So the ones on the right are the reciprocals of the ones on the left. So what would cosecant be? Yep.
Hypotenuse over opposite.
Yep. And secant would be hypotenuse over adjacent, and cotangent, adjacent over opposite. So if you memorize the 3 on the left, you automatically would know the 3 on the right. There's a trick you can use to memorize them. Sometimes people use this. Does anybody know The trick I'm thinking of to memorize the three on the left? Yeah?
Is it separate?
Okay, so can you explain what you mean?
It's like the way it's spelled like tells you what which of it is. So it's it's SOH, so it's sine equals opposite over hypotenuse, and then
Sine is opposite over hypotenuse.
and then cosine is adjacent over hypotenuse, so it's cub.
Yep.
And then toe is the T O and A.
Tangent is opposite over adjacent. Yep. So sometimes that's, I guess, an acronym, you call it. It's what people use to try to remember. Bless you. The three trig functions on the left. Okay. One time when I asked for the acronym what you can use to remember the three on the left, somebody said Sacagawea. That doesn't help. Sakatoa, not Sacagawea. And then the three on the right, there is really no acronym for that. You just memorize the three on the left. Doesn't spell anything nice when you do the ones on the right. So, Sakatoa. Okay, so now let's talk a little bit about the opposite and adjacent. Okay, first of all, opposite and adjacent are not fixed. Okay, they are what we call relative terms. It's kind of like in this room if I wanted to put labels that represented which side is left and which side is right. Well, that's relative to where you are facing. So I can't say that, like, the left wall is always at the door. If I'm facing you, it is. But if you're facing me, the left wall is the windows. So opposite and adjacent are relative to which way you are facing in the triangle. So how do you know which way you're facing? Well, what they generally do is they mark one of the angles with theta. Whatever angle they mark as theta, that is your perspective. So it's like you're standing here. Opposite is the side that's out across from you. Adjacent is the side that's next to you that's not the hypotenuse. Okay? Hypotenuse is not a relative term. Hypotenuse is always across from the knife. So in this room, that would be like, can we label a certain side as up? Yeah. No matter which way you face, up is always the same. Up. If your triangle looks like this, and they mark your reference point at the top of the triangle, then opposite would now be the bottom, and adjacent is the side that's next to the angle that's not the hypotenuse. All right, so any questions on how opposite and adjacent can switch places? Okay. But hypotenuse does not. It's always across from the knife. Okay. Does everybody have the 6 formulas, 6 definitions from that page? All right, so what I want to look at now is what happens if I give you an angle and I ask you to find a trig function of it, like sine or cosine. So let's say you had a triangle like, let's do like this, like that, and then another triangle like that. What's the word you could use to describe these two triangles? They're not congruent because they're different sizes. But yeah, they're similar. One of them is, they're both 45, 45, 90 because of the tool that I used to draw. Okay, so they're both 45, 45, 90 triangles. So the question would be, if I ask you to find, let's say, the sine of 45 degrees, what was the definition we just had for sine? Yeah. Okay, so it's opposite over hypotenuse. And then if you were to do the same thing in the bigger triangle, it would be opposite over hypotenuse. So the question is, if I find the sine of 45 in the smaller triangle, and then I find the sine of 45 in the bigger triangle, how will the two answers compare? Yeah?
Your answer should be the same.
They,
because
yeah.
It creates a ratio.
Yeah, they'll be the same. Right? So if this side was like 3 units, and let's say we did something that was like a scale factor of 2. This other triangle is twice as big. This side would be 6 units. Well, if we use Pythagorean theorem, because this is a 45, 45, 90, and we find the hypotenuse of the small one, and then we find the hypotenuse of the big one, that hypotenuse is also going to be double the size of the small one. And when you find the ratio, because everything is just double, it's going to be the same ratio. It's like taking 3 over 4 and dividing by 6 over 8. Yep, you doubled the numbers, but since you doubled the top and the bottom, the larger version will reduce to the smaller one. So they will come out the same. Right, so that's important to understand. So when you have two right triangles where all the angles are the same, it doesn't guarantee the size of the triangles are the same, but it does guarantee that the triangles are similar. If the triangles are similar, the trig functions will come out the same for a given angle. All right. So that means if I ask you to find like the sine or the cosine of a 30-degree angle or a 45-degree angle, and you're not sure how big of a triangle you should draw to figure it out, it doesn't matter. As long as you label your sides correctly, you can draw any size triangle to figure out a trig function. The size of the triangle is not important. Okay, so here's an example with sides that are accurately labeled. These are all correct. And let's say we wanted to find the sine of 30 degrees. Let's do the small one first. What would be the sine of 30 degrees using the numbers in the small triangle? Yep.
1 over 2.
It would be 1 over 2. Opposite over hypotenuse. Now, let's do the same thing. So same perspective. I want you to pretend like you're standing at this angle. What would be the sine of 30 degrees in the big triangle? Yep. It would be opposite over hypotenuse, which is 2 over 4. But it reduces to 1 over 2. So the sine of 30 degrees is always 1/2, regardless of the size triangle that you use. Big triangle, little triangle. It's always a half. Okay. Any question on that? All right, so how would you do something like this? Okay, I'm going to give you one trig function, and I want you to use the information here to figure out all the other 6. If I tell you the sine of an angle, I haven't told you the angle, but I told you the sine of it, what have I really given you here? Sine of theta equals 5/6. I've told you something. I told you a couple things that are important. Yep.
The measure of the opposite angle in the hypotenuse.
I've given you the, can you say that again?
You give me the reduced version of the measure of the opposite angle, the opposite side over
Side.
in the hypotenuse.
Yes. So what I've really given you here is 2 sides in a right triangle. Because I've given you 2 of the sides, you can figure out the third one using what? That's exactly. So that's what I'm explaining right here. So if you have to figure out all 6 trig functions and you only know one of them, take the one that you know and use it to label 2 of the sides in a triangle. If you know sine, then you can label the opposite and hypotenuse. If you know tangent, you can label the opposite and adjacent, and so on. Once you label 2 of the sides, use the Pythagorean theorem, and now you have the third side. Now you've got a triangle where you know every side, and you can figure out any trig function that you want. Generally, when we find the sides, do not want to use any decimals. So if you get a decimal, leave it as a square root, okay, when you're solving. So like, if I go back to this problem right here, if I asked you to identify how long the hypotenuse is, I'd be looking for that. Okay, it's the square root of 18, which is 3 square roots of 2. Okay, so no decimals for now. I'll let you know when decimals are okay. Not now. Okay, so let's try that on our question. Okay, so they're telling us the sine of theta is 5/6. You can sketch your right triangle facing any way you want. I just always tend to do it this way. That's how I do it. And you can put theta as either one of the acute angles. So your diagram might be different than somebody else's, but as long as you label it correctly, it's fine. If yours is a mirror image, it's still going to give you the same answers. Okay, so where would the 5 go? Yeah?
On the right side.
On the right side, which is opposite. And how about the 6? Where the hypotenuse is. So we've got to find, you can call it x temporarily, call it a, b, whatever you want to call it. But now we have to find x. Okay, so set up your Pythagorean theorem. That's 25. That's 36. When you bring the 25 to the other side, what's 36 minus 25? Yep. 11. And now we got to get the square root. And are we going to change the square root of 11 to a decimal? No. So leave it as square root of 11. What that means is one of your sides is a square root. It is possible that that side ends up in the bottom of a fraction, and we can't leave it there. So we might have to fix that. Okay. All right, so let's do the sine. Well, we already know that. 5/6. Cosine. What's the cosine of theta going to be? Yeah.
The square root of 11 over 6.
Yep, and that's fine because the square root was in the top. So no problem there. And what about the tangent of theta? Yep.
5 round 11 over 11.
Yep, 5 square roots of 11 over 11. So you might start with 5 divided by the square root of 11, but then you have to fix having the square root in the bottom. So we started with this, and then changed it. Okay, so we've got the first 3. What do we do to get the last 3? Yeah.
Wouldn't you just flip that?
Yep, we just flip them. Okay, when we flip sine, no problem there. No square roots. Cosecant is 6/5. What about the secant? Final answer. Yep.
6 round 11.
Yep. 6 square root of 11 over 11. And now the cotangent, I would think back to what we started with, because when you flip that, it goes to the top. Square root of 11 over 5. Okay, so sometimes it's not only about finding a way that works, but try to find the fastest way that works. Especially if you were taking like an AP exam, it is timed, so you have to find faster ways to do things. even if you know a long way, it might not give you enough time to get it done. Okay. All right, let's try this one. Find all 6 trig functions of theta. What do I need to figure out first? Yeah, the hypotenuse. And do you know what the hypotenuse is going to come out to here? Yeah. 13. Yeah, this is a Pythagorean triple, which means all sides are integers in a right triangle. And if you do 5 squared plus 12 squared, you get 169. And the square root of that is 13. So no roots. This one's very fast to find them all. What's going to be the sine of theta? Yeah, Hans?
Oh, 5 over 13.
5 over 13. And the cosine of theta? Yeah. 12 over 13. And the tangent of theta? Yeah. 5 over 12. And then if we flip them all, get the reciprocals, we get the other 3. So 13 fifths, 13 twelfths, 12 fifths. Now remember, what we did there is we found the 6 trig functions of theta. We did not find theta. We don't know how many radians or degrees this angle is. These equations would help us figure that out. In fact, we could just pick one of them, and that would be enough to figure it out. But that's not what we've done yet. Okay. Any questions on that one? Let's try this one. It says, use the diagram below to find the 6 trig functions of 45. Now, let's say that that's all I give you. You have to make your own diagram to figure it out. How many different size 45, 45, 90 triangles are there? Yeah?
There is one. Well, technically you can use different numbers, but the sides for both the legs would be equal, correct?
Well, the sides for both the legs will be equal, yeah, because it's always isosceles. So what are the different numbers you could use for the legs? How many different 45, 45, 90 triangles could you draw, size-wise? An infinite amount. There are an infinite amount of different size 45, 45, 90s. Does it matter what size 45, 45, 90 you draw? No, it doesn't matter. You just have to pick one and draw it. So, any suggestions what I make the 2 legs for size? Okay, we could do 2 and 2. 1 and 1 would have been even a little easier because then the numbers would have been smaller. So we're going to end up having to reduce now, but that's fine. 2 and 2. And now we have to figure out the hypotenuse. 2 squared plus 2 squared, take the square root. 4 plus 4 gives me 8. And what's the square root of 8? Yep.
2 rad 2.
2 rad 2. Okay, so you've just created a properly labeled 45, 45, 90, and you can use it to figure out the trig functions. Okay. I'm just going to do the first 3. So which 45-degree angle should we use as our perspective, as our reference point? The one in the lower left or the one at the top? Yeah?
Oh, I was well, I guess we could just use the bottom.
So which one are you using?
The one, the bottom.
The bottom one? Why not the top one?
angle you choose doesn't matter since it's an isosceles.
Yeah, it's isosceles, so regardless of which 45 you choose, the opposite is always going to be a 2. So it doesn't matter. I'll go with the bottom one because that's what Len said. And now we'll figure out our trig function. So we've got opposite over hypotenuse. So we have 2 over 2 root 2. Because we didn't use a 1 and a 1, the 2's are going to cancel now. And had we used a 1 and a 1, you would have had this as the first step. Opposite over hypotenuse. What does 1 over the square root of 2 turn into when we fix it? Yeah.
Root 2 over 2.
Root 2 over 2. Okay. What's the cosine of 45 going to be? Yeah.
It's gonna be the same thing.
It's the same thing because it's isosceles. Right? Sine and cosine are always the same in an isosceles triangle. So it's also root 2 over 2. And what about the tangent of 45? Yeah. 1. Opposite divided by adjacent, they're the same. So it comes out to 1. So you should be able to figure out all the exact trig functions of a 45-degree angle by creating your own diagram. And you should be able to do it for 30 and 60 as well. All right. So to figure it out for 30 and 60, my hint would be to start with a triangle like that. What kind of triangle does that look like? Yeah?
An equilateral.
Right, it looks like an equilateral. What do we know about an equilateral?
All 3 sides are equal.
Yeah, all 3 sides are equal in length. So we could label these sides whatever we want, but they all have to be the same number. And I would suggest labeling them all 2. We'll see why in a second. Now, to do the kind of trig that we're doing, we need a right triangle. Is there a right triangle in that picture right now? No, I gotta create one. How could I create a right triangle in that picture? And it's automatically gonna be a 30, 60, 90 right triangle when I do it. Yeah?
Draw a line from the top angle directly down to the bottom side.
Yeah, in an equilateral triangle, and you can prove this, if you draw an angle bisector that is perpendicular to the base, it automatically bisects the bottom side. This is why I made the bottom side 2 from here to here. Because now, how long is it from there to there? Yeah? It's 1. So this side is 1 unit. The hypotenuse is 2 units. And I can find the long leg, which is that side I just drew, using Pythagorean theorem. So here's the triangle you're working with. And we know that this angle in the lower right is how much? Yep.
60 degrees.
It has to be 60 because it was an angle in an equilateral triangle, and all the angles are 60. So if that's 60, that has to be 30. So 1, the hypotenuse is 2, and what would the long leg be? Yep.
Square root of 5.
Um,
Oh, wait, it's a leg.
Not square root of 5. You're on the right track. It is a square root.
Square root of
3. Yep. Because if you square that, you get 3. If you square that, you get 1. 3 plus 1 gives you 4. And the square root of 4 is 2. Okay. So now you could find all your trig functions of 30 and 60. Is there any question how you would find the 6 trig functions of 30 and 60? Just remember for 30, use that as your reference point. 1 is opposite, root 3 is adjacent. When you do 60, root 3 is opposite, and 1 is adjacent. Okay? Okay, so you're going to get very similar answers when you do the 30 and the 60. They're just going to change places. All right, complementary. What does it mean if two angles are complementary? Yeah.
They equal 90.
So like a right angle is complementary because it equals 90.
Well, two angles are equal.
So two right angles are complementary because they both equal 90.
No, two angles that add up to.
Add up to 90, exactly. So their sum has to equal 90, not the individual angles themselves. Okay. How come the two acute angles in a right triangle are always going to be complementary? Yeah.
Because one of the angles is right angle.
Right. Because one of the angles is a right angle, and we know that all the angles in a triangle
Add up to 180.
add up to 180. So if you've already used 90 for the right angle, then the other two have to also add up to 90, or you wouldn't have a triangle. All right, so the last thing. We usually use A, B, and C for sides. What kind of letters do we use to label angles? Yeah.
Isn't it X, Y, and Z?
I mean, I guess you could. You can technically use anything. It's not the convention we're going to use, though. Anyone remember what kind of letters I talked about before that are always going to be used to represent angles? Yeah?
Yeah, with the Greek letters, right?
Greek letters, yes. So what we're going to do is we'll stick with A, B, and C for the sides, and we're going to stick with Greek letters for the angles. Okay, a couple of reasons why. If we use a Greek letter, then it's a totally different symbol than an English letter. So there's no question when you write it down. It shouldn't be confusing to look at on paper because the Greek letters look very different than the English letters. The other reason is when we're talking about finding sides and angles, if I said to you, like, I want you to find A, and I was using capital letters for like angles and lowercase letters for sides, that's a vague question. Like, you'd have to go, what do you mean? You want the capital A or the lowercase a? It's confusion. So we'll stick with Greek letters for angles, English letters for sides. Not how our book does it, but it is how a lot of books do Trig. That is how we'll do it. When we set up the diagram, it is important that this Greek letter, which is alpha, is always across from A. You always want to keep those across from each other. And this Greek letter, beta, is always across from B. Notice I didn't use a third Greek letter because I don't need to for now because it's a 90. So we can call it a right angle. When we start studying trig that's not in a right triangle, we're going to need a name for that third. Not right now. So A across from alpha, B across from beta, just to keep things straight in our head. All right, let's try something. Let's find the sine of alpha. What would the sine of alpha equal in that diagram? Yeah?
A over C.
A over C. Now I'm going to do a different question, but it's going to be connected to the first one. I want to take the trig function that I have and put the word co in front of it. What trig function do I get if I prefix this with co? Yep.
Cosine.
Cosine. So let's do the cosine. And I don't want to do alpha. I want to do the angle complementary to alpha. What angle is complementary to alpha in that diagram?
Beta.
Beta. So I put the word co in front of my original function, and I found the complement of alpha. What's the cosine of beta? Yep. It's also A over C, adjacent over hypotenuse. Came out the same. Let's do another one. Let's do the tangent of alpha. What's the tangent of alpha? Yeah.
B over it.
That's the cotangent.
So
A over B. Tangent is opposite over adjacent. Okay, so now let's make up another question. What trig function do you get if you prefix that with co? Yeah, cotangent. And the angle that is complementary to alpha, we just said that earlier, is beta. What's the cotangent of beta? So you're looking for adjacent over opposite, and you're standing at beta. Yeah.
Would just be
Be A over B. So there's a pattern here to these answers and why they're coming out the same. And it has to do with this theorem. It's called the complementary angle theorem. It's very simple. It says that if you have co-functions, a co-function is when you put the word co in front of a trig function. Right? So if you have co-functions and you have angles that are complementary, they will come out equal. Okay? So we're going to try this with numbers now, not just letters. What's the co-function of sine? What function do you get when you put co in front of sine? Yep. Cosine. How about, what's the co-function of secant? Yep. Cosecant. And the co-function of tangent? Yeah. Cotangent. Those are the pairs of co-functions. Now, if I asked you for the co-function of cosine, don't say cocosine. That's not a thing. The co-function of cosine is sine. All right, so let's try, so let's do this. I don't know what the sine of 15 degrees is. All I want you to do is write something that it's equal to, based on this theorem. Anyone think they could give me something on the right side that sine of 15 degrees is equal to? Yeah?
Cosine of 85.
Cosine of
85.
75. So sine, cosine, cofunctions. 15, 75. Complementary. Because you have cofunctions of complementary angles, they will come out the same. Okay. Sine 15, cosine 75. Same thing. So why would that be useful? Well, let's do this. I'm more interested in the y than the actual answer here. The sine of 35 minus the cosine of 55. What would that come out to? Yeah?
Wouldn't it come up to 0?
Yes, the answer there is 0. How come?
Because the opposite of cosine is sine of 55. Or
Okay.
cosine.
Careful, make sure we use the right words.
Yeah.
The,
The opposite of cosine 55 is sine 35. and sine
okay,
35
these aren't opposites. They are,
reciprocals.
no, not reciprocals. Yep.
Co-function.
Co-functions, yeah. Okay, so sine and cosine are cofunctions. So we got that part. And then what else? Just having a sine minus a cosine isn't always 0. It has to be very special, like this one. Yeah.
The complementary.
You have to have complementary angles. So if you have cofunctions of complementary angles, we know they're equal. I don't know what this is. I don't know what that is. But I know they're the same. And if I subtract two things that are the same, I get 0. How about that one? Tangent of 20 degrees divided by cotangent of 70 degrees. What would that come out to? Yeah.
Would that be 1?
Yeah, it would be 1 for the same reason. These are cofunctions, these are complementary, so you're dividing two things that are the same. I don't know what either one of them is. I know they're the same. All right. So that's first part of 6.5. So the homework is mostly in the book, but the last 2 questions are like what we just did on the board. They're very quick. So make sure you do the 2 simplifies as well.